Hello, I'm Dr. Gavin Travers. I'm an internal research fellow at the European Space Agency from the European Astronaut Centre in Cologne. And we are here on this campaign with a collaborator, Professor Eric S.T.A.R.L.I.N.G from the University of Leibniz, Hanover, in the Institute of Sports Science there. The purpose of the project is to validate the performance of a potential candidate hemodynamic device that we think might be useful in future spaceflight. And it is this device here called the S.T.A.R.L.I.N.G SV. So it's a commercial-based device that involves 4 sticky patches on the torso and passes a harmless electrical current between them. And the device is used looking at the impedance of that signal between the electrodes, and then based on its algorithm is estimating the blood that traverses the thorax, and then non-invasively then is estimating the volume of blood pumped by the heart with each beat. And the reason that that's important for astronauts is we need to monitor their cardiovascular health, as well as look at things like their cardiorespiratory fitness, which decreases to quite some extent in long-duration space missions. Now, the problem that we have is that we have, currently on ISS, we have several methods for monitoring heart function and stroke volume, and that includes things like ultrasound, which is quite tricky to do. We have to train the astronauts. And the other are these 2 devices down here on the bottom shelf that place a finger cuff on the finger and measures the blood pressure with each beat and then estimates the stroke volume that way. But then the issues with that is they're quite clunky and reduces what the astronauts can be doing. And in certain situations when the astronaut stops being an astronaut and becomes a patient. We have done several experiments with the device already. Now the next logical step for us is to assess whether we can compare if the values are changing when they should be changing against another method that we currently use in space. So what we have is the seated position where we will have an individual for 15 parabolas, where we compare finger cuffs to the S.T.A.R.L.I.N.G, and we also compare it to the ultrasound of the heart. And what there is because there is a gradient between the head and the feet. With the pull-up phase, we should experience blood flow or blood being traversed towards the feet, and then in the 0G, it's coming back up towards the thorax. So we should see a change in the stroke volume, and we compare that to, as a specific check, to on the other side of this rack is we have a supine mattress area where there is no gradient between the head and the feet, and so we should not be seeing fluctuations in the stroke volume or the fluid content within the thorax with each parabola. So we're using it as a specificity check of the device. We don't want to see lots of noise, and that tells us it's detecting what it should be detecting, and we're therefore confident that it'll be useful for pre-flight ground measurements and then changes that would occur in spaceflight. So currently on board ISS we have, as I've mentioned, we have various methods of measuring the stroke volume of the heart. Some of them use a lot of resources and need a lot of space and power. Whereas the plan for the Artemis program for when the humans start flying is to have something called the XMS, the Exploratory Medical System. And that is to be a very small and compact multi-component device that has several different things that can do as many things as we can with a very small requirement of power and consumables. And one of those things that we don't have within that system at the moment is something that can monitor the cardiovascular function directly. So we have things like blood pressure, temperature, glucose monitoring is all integrated, and then there is a single communication stream via ESA to the Earth. So we want to put everything together, and the S.T.A.R.L.I.N.G SV should be compatible with that device.